Hi, everyone. I'm really excited to be here today at the Ray Summit Connect event to give a talk on demystifying neural architecture search in theory and practice. So I want to just give a brief introduction about myself before we get started. So my name is Liam. I recently graduated with a PhD in machine learning from CMU, and since then I've joined Determined as a machine learning engineer. And this talk today will be sharing some of the insights that I've gained about neural architecture search, both in sort of the research that I've done and also more recently at Determined. Now let's get started. So whenever I train a neural network, say I'm training a network for image classification, I always find myself wondering about certain questions, like how should I design this network? What activation function or pooling method should I use? Where should I put a skipped connect? Should I just use some pre-canned architectures like ResNet or VGG? Or can I actually find more specialized architectures that would actually perform better for my problem? These kinds of questions are kind of the exact questions that we want to be able to answer with recent work in this field of machine learning called neural architecture search. And we've seen a lot of interest in neural architecture search from some of the largest tech companies who have published papers in the area and also offer NAS solutions in some of their cloud platforms. And in the previous talk, Richard shared with us how to do hyperparameter optimization with RayTune. And we all know that hyperparameter optimization is a large part of AutoML, but where does neural architecture search fit into this picture? So the stated goal of NAS is to automate architecture design, but in reality, it involves searching through basically a large space of possible architectures. So from our view, NAS is a special case of hyperparameter optimization. And the first generation of NAS methods were able to achieve state-of-the-art results on two common machine learning tasks, image classification and language modeling. But they did so at tremendous compute cost. So for the result on CIFAR 10, it required over 3,000 GPU days in order to find a good architecture. And for the language modeling task on PenTreeBank, it required over 10,000 CPU days. And it was very expensive to get these results because it required training thousands of architectures from the search base before finding a good architecture. More recently, we've seen weight sharing emerge as a more efficient method for NAS. And the way that weight sharing works is you basically have a single weight sharing network that you can use to evaluate all possible architectures in your search space. Hence, the search cost is reduced to that of training a single network. So let's pull back the hood a little bit and see what is happening in weight sharing. So the way that weight sharing works is it's a single weight sharing network that includes all possible architecture choices. So here, the GIF on the right is basically demonstrating that for the search space that you could consider, there are 4 possible operations that you can use for every single layer. So here it's con 3x3, con 5x5, pooling, or skip connect. And if you were considering a single architecture, you would pick one of these operations for every single layer. But with the weight sharing network, it includes all operations, all possible operations at each layer. And there are these architecture parameters alpha that basically are the parameters that we learn in order to find a good architecture within this weight sharing network. So by including all the possible choices and all the possible operations in each layer, the weight sharing network also includes all possible architectures as subnetworks. And in this way, training just the weight sharing network, we're able to use the architecture parameters to get a signal about what a good architecture is from the search space. So you might be thinking, this is hocus pocus. How does this even work? Won't the subnetworks from the weight sharing network interfere with each other? And you might have also heard that it's crazy that weight sharing works because the weight sharing performance of standalone architectures has low correlation with the ground truth performance when you train those architectures from scratch. So in this talk, I'm going to attempt to sort of demystify weight sharing through the lens of optimization. And in the second part, we're going to put our practitioner hats on, and I'm going to sort of talk about how we can apply NAS in practice with Determined, which is an open source deep learning training platform. So for the first part, understanding weight sharing through the lens of optimization, some of the key questions that we had were, are these weight sharing approaches guaranteed to converge? And in this talk, I won't have time to go into the details of our work, but I will try to give some high level intuition for our conclusions here. So the answer to this first question is that yes, these approaches are guaranteed to converge, and we are able to analyze the convergence rate through the framework of mirror descent. Second question we had was, how can we design faster and more accurate NAS methods? And we showed that we're able to take a geometry-aware approach to design a new algorithm called GAEA that has provably faster convergence rates than standard NAS algorithms like DARTs. And finally, does taking this geometry-aware approach improve performance on actual NAS benchmarks? So let's see. For the DART search space, on the SAFAR 10 dataset, we see that our GAEA approach is able to achieve the best result on this search space. And the results highlighted in orange are sort of algorithms, standard hyperparameter optimization algorithms, while all the other algorithms are sort of NAS-specific algorithms. Also for the DART search space on ImageNet, here the first two rows show basically the performance of the first generation of NAS methods that used full training in order to find a good architecture. And recently we've seen that weight sharing NAS methods have been able to match the performance of the best sort of first generation full training methods. So here we can see that PC Darts was able to recently match AmoebaNet on ImageNet. And with GAEA, we're able to improve upon the PC Darts results even more and reach state-of-the-art on ImageNet for this benchmark and this search space. We also looked at the NASBench 201 benchmarks, where in this benchmark, the results for 3 different data sets are provided, and the authors study the performance of standard hyperparameter optimization methods like random search, reinforcement learning, and Bayesian optimization hyperband, and also compared sort of recent weight sharing methods to standard hyperparameter optimization methods. And what they found was kind of surprising, which is that the standard hyperparameter optimization methods actually outperformed the weight sharing methods. When we evaluated GAEA on these 3 data sets, we surprisingly saw that we were able to beat not only all the weight sharing methods, but also the standard hyperparameter optimization methods and approach the optimum architectures in each of these 3 data sets. So what is GAEA doing, and why does it work so well in practice? So in order to understand that, we have to first understand the weight sharing optimization problem. And so if we start with the original optimization problem solved by first generation NAS methods, the objective that they solve is basically this bi-level objective where we want to find the architecture that has the lowest loss from the search space, right? So here, the objective is just saying configure a certain model M according to an architecture alpha, and then find the weights that minimizes this loss, and then choose the architecture that has the lowest loss. So here, just as a reminder, these first generation methods train many architectures individually and adapted the architecture distribution after receiving some signals about the performance of different architectures, and would finally return the best architecture. In contrast, the weight sharing optimization problem is a single objective where we have a weight sharing network M that is parameterized by both the weights of the network as well as architecture parameters theta. And the architecture parameters theta is a continuous relaxation of the original architecture space A. And the weight sharing methods optimize both W and theta simultaneously using gradients. So when you look at this new optimization objective, it looks very similar to the objectives that we work with in standard neural network training, where we're able to apply gradients in order to update the parameters. So exactly, so theta is a learned parameter like W is. The way gradient-based weight sharing methods work is that they optimize both W and theta alternately. So first we fix the architecture parameters theta, and then we update W, and then we fix the network parameters W and update theta. So in the case of the DARTS algorithm, the update rule used for the architecture's parameter theta is based on the atom optimizer. And our geometry-aware exponentiated algorithm, GAEA, is a simple modification of the DARTS algorithm. Instead of using atom to optimize the architecture parameters theta, we use the exponentiated gradient update instead. And this simple modification, as we've seen, leads to significantly better results in practice. And the insight for using exponentiated gradient comes from our convergence analysis. And in our paper, we analyze the convergence rates for different gradient-based weight sharing methods and show that these convergence rates depend on the number of edges in the search space and the number of operations. So the takeaway is that our algorithm GAEA has basically less dependency on the or weaker dependency on the dimension of the search space. So in this case, we see that DARTS has convergence rate E times O, whereas GAEA has convergence rate E log O for the DART search space. And even though this gain is modest, we are able to see significant performance improvements. So do we actually observe faster convergence in practice, given what the theory suggests? And in these two charts, I'm showing the entropy for two search spaces, comparing both DARTS and GAEA. And you can see that the entropy does decrease faster for GAEA, suggesting faster convergence. So now that we've sort of taken a deep dive into the optimization problem associated with gradient-based weight sharing, some of you might be wondering, how do I actually apply NAS in practice? So in this next section, I'll talk about how you can get started with NAS with our open source platform, Determined. And I'll cover each of these 3 points in more detail next. So if you go back to the first set of experiments that I showed, one observation is that ASHA, which is an early stopping-based hyperparameter optimization algorithm, is a very strong baseline for NAS. And the surprising thing is that ASHA works out of the box and no tuning was required for the algorithm. In contrast, weight sharing methods often require a significant amount of tuning, and actually behind the scenes, there's a lot of computation going on. So what are the current drawbacks with weight sharing methods? So the first drawback is that the weight sharing network is sensitive to initialization, and as a result, multiple search runs are required to find a good architecture. So we don't train just a single weight sharing network in order to find a good architecture. We wind up having to repeat this process 4 times in order to be more robust to the weight initialization of the weight sharing network. A second drawback is that the shared weights do not quantify the standalone performance of the architectures. So the resulting architectures that the weight sharing network finds need to be retrained from scratch in order to provide the final result. So in the case of the DART search space, the retraining process required 600 epochs, and this is done for each of the 4 final architectures that were found by the weight sharing network. So there is a lot of computation going on. The third drawback is that state-of-the-art NAS methods are sensitive to internal hyperparameters, and therefore they're not robust and are fairly difficult to apply to new problems. So if we go back to the NASBench 201 results, we saw there that weight sharing actually underperformed random search, which is a standard and very standard baseline hyperparameter optimization method. And this suggests that weight sharing is not ready for prime time just yet. And right now, I think the easiest way and most robust way to get started with NAS is basically to run an early stopping method like ASHA on the NAS problem. So ASHA is an algorithm that is available within Determined, and you can go and try it out on the Dart search space. And these 2 results here, we're comparing a few different hyperparameter optimization algorithms on the 2 search spaces considered by Darts. So the CNN and the RNN search space. And we see that ASHA outperforms 2 other early stopping hyperparameter optimization methods. So you can go and try this out yourself if you want. The next observation is that reproducibility is still a challenge for NAS. So if we look at the results for the Penn Tree Bank dataset using the Dart search space, we see that there are kind of different signals coming from different papers. So the first observation is that there are 2 random search baselines provided by the ENAS paper and the Darts paper present different results. The second observation is that when we tried to reproduce ENAS, we actually got a significantly worse result than the original number published in the paper. And the fact that reproducibility is hard for NAS is not challenging, or is not surprising, because NAS algorithms, as we've seen before, require a lot of tuning. They're sensitive to random seeds, and there are also a lot of compute environment factors to track, like GPU type, CUDA version, deep learning framework, Python version, and the list just goes on. So how can we use Determined or a similar deep learning platform to improve the reproducibility of NAS? So some questions that I found myself encountering while I was doing NAS research were things like, which TensorFlow and CUDA version did I use to run these experiments? Which version of the code did I use to get these results? And which checkpoint actually gave me the best result that I found from a bunch of different runs? So before Determined, my experiment tracking was done in my file system, and that was somewhat of a nightmare. And with Determined, you're able to track these things a lot easier with features such as containerized training, where your experiments are run within a Docker image. We also offer experiment tracking, where the exact code that is run is saved and associated with each experiment. And also checkpoint tracking with Determined allows us to associate checkpoints with each of our experiments as well. So with a platform like Determined, you're able to reproduce your experiments with the click of a button. The third observation about NAS in practice is that many NAS methods require training the resulting architectures from scratch. And this can be very expensive and time consuming. So if we go back to the ImageNet results that we showed in the beginning, the GAEA architecture that we found required training on 8 NVIDIA V100 GPUs for around 70 hours, which costs $1,500, and required writing native PyTorch data parallel code without Determined. And with Determined, we're able to make it much easier to do distributed training, and we're also able to reduce the cost tremendously with preemptible instances. So if we look at the single node result for Determined, on preemptible instances, the cost is reduced to just $500. Determined also makes it easy to distribute training across multiple nodes. So you can train on 16 NVIDIA K80 GPUs and get about the same performance, but only use $250. And that also means that you can use distributed training and better GPUs to speed up the data parallel training. So that's it for my talk. And if you're interested in any of the things that I brought up in the slides, please check out our papers for more details. I'd like to especially thank my collaborators on each of these papers. Feel free to take Determined for a test run. It's an open source project, so you can just download the code from GitHub and spin up your own cluster and start trying NAS out. Thank you.